If you have a car collision, and two cars hit each other, and I compare the situation just before the collision with just after the collision. Here are the two cars, and one has a speed in this direction, the other has a speed in this direction, and they hit each other. And they stick together. That's a given. They go one big clump. So this is before, and I can give them some velocities. This is the speed of one, v1, and this is the speed of the other, v2. Afterwards, you see something like this, v prime, just a wreck. The impact time is so short that the change in momentum due to friction with the road, that would be an external force friction with the road, that can be ignored. It's negligibly small. The cars hit. There is a huge internal force going on. One slams on the other and the other slams on one. There is even fireworks. Metal scrapes over metal. Friction, but that's internal friction, not friction with the road. So momentum is approximately conserved if we can ignore the friction from the road during the impact, because the impact time is so short. So let here be car with mass m1, and here is the other car with mass m2, and we'll make it a two-dimensional problem, because we have seen only one-dimensional problems now. Let's make it a two-dimensional problem. So this is the direction for this car, and let's say this is the direction in which the other car is going, velocity v2, and tragedy has it that this is the place where they're going to collide. In what direction and what will be the speed after the collision? I only compare just the moment before the hit with just the moment after the hit. What comes later is a different story. When you have formed a wreck, clearly it's going to slide on the road, and then there is an external force, which is friction, which will slow it down. It's just during the impact, I claim, that to a reasonable approximation, momentum will have to be conserved. And so, what is the momentum of this one? Well, this may be the momentum of this one. It may have a very small mass, small speed. And what is the momentum of this one? Well, this may be the momentum of number one, and this could be the momentum of number two. The net momentum is the vectorial sum of these two, which is this. That is P total of the system. That is never going to change. That's before and after the collision exactly the same. And therefore, if you knew this angle theta, and you know P1 and you know P2, then you can calculate in what direction the objects are going to slide. But of course, you can also calculate then the velocity after the impact, because this total momentum must be the sum of the total of the two cars, the mass of the two cars, times v prime. And so you can calculate everything, and that's what the police is doing when they find wrecks on the road. They actually use the track, the skidding tracks of the wreck to calculate v prime, and then they can try to reconstruct the situation as it was before the collision. Now, in all these cases, the objects stuck together. We've only considered cases where they stick together, in which case we call those in physics completely inelastic collisions. Now, next lecture, I will also deal with situations whereby, during the collision, the particles bounce off each other. In completely inelastic collisions, you always lose kinetic energy. Sometimes a little, as you see there. Sometimes a lot, as you see there. Sometimes everything, as you see there. Always in inelastic collisions do you lose kinetic energy.